So let's continue in our study of the spring mass system, and let's this time take a look at free damped motion. Okay, free of course means that there's no driving force. Damped means that we introduce this frictional force. It could be a viscous force, it could be friction between a surface and the mass. But in any case, we're going to say that this frictional force is proportional to the velocity, or the first derivative of position with respect to time. It's negative because it opposes the motion, and beta is the constant of proportionality. So we will get this differential equation. We have from Newton's second law, ma is equal to F net, or the sum of the forces. A is the second derivative of position with respect to time, and here's the mass. And now we have two forces acting. Okay, and here's our spring force, and here's our resistive force. Rearranging and defining new parameters lambda and omega squared, as you see here, with omega squared there and 2 lambda. And we do this just so that the form of the solutions, the zeros of the auxiliary equation, are easier to express. We get these two roots or zeros of the auxiliary equation corresponding to this differential equation. And now we have three cases to consider, depending on whether we get two distinct real roots, one repeated real root, or two conjugate complex roots. So starting with the case of lambda squared minus omega squared being strictly positive, we have what's called an overdamped system. Okay, we get two distinct roots here, and the general solution is as we see here. Okay, that's just from our study of differential equations with constant coefficients, because these are constants. Okay, even though they're letters, they are constants at the end of the day. Okay, so we get this general solution, and let's consider an example. So we have this spring mass system with the parameters that you see here and the initial conditions there. So just using the differential equation, we get this homogeneous differential equation with constant coefficients. We could identify 2 lambda with 5, omega squared with 4, just from looking at the equation. And we get that lambda squared minus omega squared is strictly greater than 0, is positive, it's 9/4. And so the system is overdamped, and we get this solution. Now we want to fix these constants, C1 and C2 of the general solution, and we do that using the initial conditions. So if we take the derivative of this and plug in 0, we get that. And if we take this and plug in 0, we get this. And from both of those, we get C1 is equal to 5/3, C2 minus 2/3, and we get this solution to the initial value problem. Note here that in general with overdamped systems, you could get a situation where you get something like this, or if you could even start at the bottom and come up and go down. Okay, that's how overdamped systems behave, but you don't get this kind of oscillatory motion. Okay, we could even have a situation where kind of the reverse of the other one, something like that.